good. All right. So I also, Derek reminded me that I forgot to upload the access link to Friday's lecture on Carmen. It's now uploaded, so I think nobody else wanted to watch, so that's good. Didn't know. I gave the access link. The next week is the exam, Monday. I will post more practice problem of Jacobian. All right, later this week. I have 2 examples already. I'm gonna add 1 more. So hopefully you should feel comfortable after just solving those. I know a couple of you asked me, I didn't have time, but I'll do that. Then hopefully this week we will finish the Lagrangian at least. So today I wanted to do the explicit method, but then I realized I should solve a problem like more different from 2R robot before I go to explicit, but you will solve the same problem using the explicit method so you can compare. So that will give you a better idea of what's going on. And then on Friday, hopefully touch base on Newton-Euler method and exam review. So I'll design the questions and then as usual give you access to a sample exam. And then you will have time to just go over it quickly. But I would guess that would be a good practice for you when you're studying on the weekend. I'm assuming everybody's going to study on the weekend. Same as last exam, 1-page cheat sheet, no solutions, just the equations. And you can write in English if there's something conceptual. There will be concept again. So I don't know if you saw or not, I designed a quiz for today that will open today. But it's already open, but you need an access code and closes Wednesday by class time. So the question are more conceptual. So give you an idea of what kind of question you might see in the exam. There you have 2 chances for that quiz. Just read it. And if you have the book, I think reviewing the book will be very beneficial. If not, we have talked about it in the lecture, all the questions. All right. With that, also, I didn't have access to my OneDrive today. I don't know if any one of you had the same problem. So I couldn't annotate the lecture. I have to do later tonight. So that would be posted a little bit later. But I got the chance to fix it, whatever it was a problem. Does anybody have the same problem? Not accessing your OneDrive, or you don't check it on daily basis? You don't, okay. Oh, start broadcasting, okay. So for your class participation solution, I wrote it, but I didn't get a chance to write it on my iPad, so I would upload because I didn't have access to my OneDrive. I'm gonna go over it quickly at the beginning of the class. I think I'm gonna give everyone, or I did, based on completion, unless you did something really wrong, then you lost points, right? Okay, so a quick review of what happened last class on Friday. We talked about kinetic and potential energy. Kinetic energy is work done by bringing system from its rest, which is at where the potential energy exists, right, to its current position. We could have, hopefully this pen doesn't die today, linear motion, so kinetic energy due to the linear motion. We would say that K would be 1/2 mass times the velocity squared, right? mv squared. And this is when v is the linear velocity. Don't know what the noise is about. And then we also have rotational motion, which is due to the angular velocity of the object. Then the kinetic energy would be 1/2 I omega squared. I think when I was writing the class, I forgot the square, but it is in the annotated lecture. So omega here is your theta dot, right? So this is the angular velocity. So in Friday's lecture, I solved the Lagrangian for 2-link robot, right? And CP was 1-link robot. Now, if you have done your CP, just finding the linear velocity kinetic energy is fine, because that's what I did in the lecture. I wanted to do that. But if you also included the rotational motion, it's also correct. You're gonna today now cover the whole thing. So it is fine if you haven't done the rotational motion for your CP. Now, both of those, and we discussed, is when we had one link. If we have two link robots for the for linear motion, what would be the kinetic energy for two link robot? K1 plus K2, the kinetic energy of the first arm, and then the second arm, you add them together, right? Same for potential energy for the first link and second link. So as many link as you have, you will add these their kinetic energy. Now with rotational motion is slightly different. So when you have a one degree of freedom, or let's say one dimension, right? Like the point mass that we did, the rotational motion, your I is a scalar, just one I. But when you have multi-body, like the 2R robot that we had, then your I becomes a matrix. So it will be the tensor of inertia. Now, for rigid body object, when I write rigid body, I mean multi-body objects, right? We will write the rotational motion, the kinetic energy from rotational motion as such. We will say that K would be 1/2 omega transpose IC omega. So IC here is tensor of inertia and is in matrix form. So I didn't discuss it because I was going to do it today. That's why in your CP, if you didn't consider it, it's fine. But from now on, when we are writing the kinetic energy, we're considering both of them. We're going to look if our robot is exposed to only linear motion or is also rotational motion. So when you have a revolute joint, right, you have a rotational motion, but then your next link might be prismatic joint, right? You should be able to know what is happening, what kind of kinetic energy you might have because of the type of joint. So we are going to write, we're going to say Ki, so which for each link would be 1/2. I'm going to write the linear motion the same way, same structure as my angular motion, so it's easy for you to remember. So MIVCI transpose VCI, because if it is multiple, it means matrix, right? Your velocity also. And plus 1/2 MI, sorry, not M, this is the rotational motion. Okay, this is not happening. Omega I transpose ICI omega I. So this ICI is the tensor of inertia at center of mass, and this one you also find at center of mass. So this would be the equation for kinetic. So we will add the linear motion, kinetic energy because of linear motion to kinetic energy because of rotational motion. Now, let's say if we had two links, then K would be K1 plus K2. Just place I, 1 and 2, and then one frame to other frame, we will walk basically and write these. So K becomes sigma Ki's, I from 1 to N, and is number of links, frames, whatever you want to call it. All right. We also introduced, I introduced Lagrange equation, right? So do you remember the equation? So there's the Lagrange equation and there's the equation of motion from Lagrangian method, right? They're two different things. The Lagrange equation L is K minus U, which is kinetic energy. So the system overall kinetic energy minus the system's overall potential energy. That will give you the Lagrange equation. Now, to get the equation of motion from Lagrange equation, we will perform that operation. The derivative of, so we will get first the partial derivative of L, the Lagrangian, with respect to Q dot, all the generalized coordinates. Then we get the time derivative of that minus partial differential of our Lagrangian function with respect to all the q's now. That will be equal to tau, which is our generalized torque or force. There might not be that, those are the external. So there might not be any external, then it becomes zero, equal to zero, right? But if there was any force or torques, then we will put it on the right side of the equation. So the right side of equation is the external force and torques. The left side is because of our system itself. Now gravity is because due to the, for example, mass of the system. So it is it's not internal, but we will put it on the left side because it's applied to the system. But if you have a motor that has certain torque and is applied to that length, that torque is going to be on the right side, right? Because it's an external torque. Make sense? All right, so we could write the kinetic energy in form of the quadratic form. You will see this on Wednesday more in detail, but you can write 1/2 q dot t m q dot. And do you remember what m was? Mass matrix. So you'll see that the both inertia and mass properties will appear in mass matrix. Do you remember the dimensions of mass matrix? How does it relate to your system? Yes, or number of bits, yes, number of masses. Then the potential energy for rigid body motion that is frictionless, if it is, it will be only gravity. But let's say a non-rigid, let's say you have a spring in your system, there's torsion. So when there is torsion, when there is like there are two links, there is a torsion between them, the system is not rigid body anymore, right? So you're gonna have this potential energy coming from this spring, right? But we have in a lot of our system, for example, if you have motor, you might have that spring in your motor when it's connected to the link. So we have to count that into account. I'll try to bring an example for both of these cases, but for rigid body, we will only assume gravity vectors. But in real life, when you actually have the real system, then you have to think about other source of potential energy, right? Okay. So hopefully these are all review. Let's get to the general formula of equation of motion. What is Q? And so I want you to remember this general form. You might be asked to write it. What is Q here? The generalized joint variables, right? Joint coordinates. What is the noise? Generalized joint coordinates. Q could be Q1, Q2, Qn. These could be prismatic joints or revolute joints. We are going to just call them Q. What is M? M we just covered is the mass matrix, which is symmetrical, positive definite. Does anybody know what positive definite is?
Every entry is above zero.
What?
Every entry is above zero.
Every entry is non-negative, right? It's positive, and also you could find a vector that if you multiply by that, it's going to be always greater than zero. Semi-definite, you could have zero.
Yeah, that's
Semi-definite, yeah. But we're just full positive, definite, you only have positive values. Okay, so, and this is n by n. What is V Q Q dot? So the equation is n Q Q double dot plus V Q Q dot. So that V is function of Q or Q dot, and Q dot plus GQ is tau. So MQ is mass matrix. Q double dot is acceleration due to inertia, right, of the system. Now what is VQQ dot, or previously I used H QQ dot. What is that curve? Yes. So Q dot is velocity of each joint, right? What is that D function or H? What are we representing? Let's do these two, so see what we will left with. That might help. What is GQ? What does that represent? Gravitational forces. What is tau? External, so generalized. External torques and forces. So when I say generalize, it means that I can put force there, right? It doesn't have to be necessarily torque, but it could be also torque. So either or, it will be encapsulated as tau. You're generalizing it. Now, what is the remaining? So we have inertia, like we have mass matrix, and then the acceleration because of the acceleration of those masses. We have gravity, tau, and then what was V representing? What did V represent? So positive definite, all elements of that matrix are positive and non-zero. So there's no negative entry. It is semi-definite, you might have some zeros. There's also, you can define a vector that if you multiply by the matrix is always greater than zero. For more detail, because there's a whole lot of math going on with positive definite and semi-definite, semi-positive definite, you can Google. Right. So do you remember what V was? Do you remember? Yes. So yes. So if you remember the example of the 2-hour robots, some term had theta dot multiplied, right? So they were quadratic form. For example, if you have two links, you have two joints, you have theta dot 1, theta dot 2, the production of the product of the velocity, theta dot 1, theta dot 2, will appear in that term, right? So Coriolis forces and centripetal forces are going to appear and be bundled up in the V or H function. We will introduce that term as centripetal and Coriolis. Now, so when we have the quadratic form of that, when it's theta dot 1 times theta dot 2, so it's like two velocities multiplied by each other, right? So it creates a force. So we have centripetal force and then Coriolis force. So whenever we have force, there's an acceleration, right? So they act like acceleration, those terms. So if theta double dot is 0, if the system doesn't have any acceleration because of the inertia doesn't, like if your velocity doesn't change to acceleration 0, it doesn't mean there's no other acceleration in the system. There are those quadratic forms. Because if you don't have them, then if you are rotating the mass, it's going to skip, right? It's going to go away. So they are kind of keeping the mass. So when there is force, then you have an acceleration. But here they are in terms of the product of the velocity. Now, if you have here Q I dot square, these are the centripetal force terms, centripetal terms, I'm going to say. Then if you, so that's one. If you have Q dot I, Q dot J, then I is not equal to J. These are also product of velocity, right? These will represent Coriolis terms. So having theta double dot equal to 0 doesn't mean there aren't other kind of acceleration in the system. It's just not because of the inertia of the system, right? It's because of product of the velocity. All right. So these two, this basically is the whole your joint space dynamic. It will also apply to other dynamical systems, but we're just going to concentrate on our manipulator. Now let's take a look at a different manipulator. We want to find the equation of motion of an RP manipulator arm, we want to use Lagrange formulation. So here, as you can see, we have the tensor of inertia. IC1, I'm going to write those down. IC1 here is, let's say IXX, IYY1, IZZ1, and the other ones are 0. And then for IC2, we are gonna assume it's gonna be IXX2, YY2, and the other ones 0. Okay, so let's say, so now we know that we have to use them in developing our kinetic energy. So we want to find the equation of motion of this manipulator arm using Lagrange formula. Let's take a look at this robot. So at base frame, we have our first joint, which is a revolute joint, right? And then we are assuming the center of mass to be L1. The mass is M1, and then the next joint, we have a prismatic joint with mass 2, and we are going to assume that we're going to base our work calculation from the center of mass in object 2, right? You'll see that here, this notation is 2 arrowhead line shows your dt, so this is your second joint variable. The thing is, here, this distance is measured always from the base frame in this example. So we know that we always start from here, right? So this distance is always fixed, whatever that is. But the question is telling us the system, don't worry about that. Always assume your d is being measured from the base frame, right? So when you're solving a problem, you have to look at what the problem is studying, right? So the configuration of robot and all the values given are as such. So when we are calculating our dynamic, we are going to always think that our prismatic joint is measured from here, but we know in reality, the only time it changes is from this distance and above. But this is for simplicity. We measure it from that point. I just want to have a simple example. Now, what would be our approach to find the equation of motion from Lagrangian formula? What are the steps we're going to take? Anyone? Someone else? Everybody else? Let's see. No, you've been answering a lot of questions, which is good. I will always count on you raising your hand. See if anybody else knows. We are going to use Lagrangian method. Okay, what is that thing? Oh, so, okay, you mean the Q? What is our Q? So the generalized coordinate. So here is what? Theta 1 and? Someone said D2. So first define what are your generalized coordinates, right? So if we replace Q for them, you know what they are. We could also use theta 1 and T2, doesn't matter. But good. So what I'm asking is, we are going to use Lagrange formula, right? The method is being given to us. We have to do that. So what are the steps in using Lagrange formula? As part of it, yes. I want you to think like big. When I solve the problems, I've solved at least one problem, right? Where did I start? What was the approach? I want you to think about the approach. If you don't have the approach, like the steps, you can't focus on calculating each part. You'll be overrun, like, what am I doing right now? So the question is, so first you have to find the Lagrange function, right? That is, so if you're using Lagrangian, we need to have Lagrange function. So this is your approach. Find L, right? Which L was what? K minus U, right? Now what's the next step from here? Find K, find U, right? That's your next steps. Then what? Andrew. Then what? So what is it called? The equation of motion? Yeah. Which was ddt partial of L respect to Q dot I minus respect to Q. This is your approach now, right? So the rest of it is just doing math. First, we're going to start from K, which is the kinetic energy, right? Let's find the kinetic energy. We know we have two links, right? We have two joints, two links. So we are going to have K1 and K2. So let's start writing K1, then K2. We're going to have U1 and U2. Once we have those, we're basically done. The rest is just getting partial derivatives. I mean, it's the hard part, but this is the easy part. All right. So we know we have to do K1 and K2. So since we have both linear motion and angular motion here, we are going to add the linear kinetic energy and the rotational kinetic energy. So for the first one, the first object is this. Well, the first link, right? So this is M1. This is measured as L1. We have also IC1, and this is our theta 1. So right hand rule, Z is out. So that's our frame one. So K1 is 1/2 M1 L1 square theta dot 1 square. Now remember from the, yes. So that's what I'm gonna say. So remember from the example we saw, you could find the velocity in x direction, the velocity in y direction, then when you add them up, you have sine squared theta plus cosine squared theta factor out L1. So that is basically the length. So I'm just simplifying it. Yes. So because you have two axes, right? So when this rotates, you always have a velocity in x direction and y direction. You could go from there, so find x and y of that center of mass. So you could either find x1 c1 y c1 and find x dot c1 y dot c1, then 1/2 mv squared. Or since you have already done it, you know that you're gonna have this form. So I just wrote this form, right? So this is the linear velocity, right? It's not just because of the linear motion, because you will have velocity in x and y direction. Because our frame is an inertial frame, right? So if an object is moving, your velocity is going to be in x and y direction. Because velocity is a vector, you will have a magnitude, and you have a vector that will show the direction of that, which will be in x, y, and z direction. Your z direction is 0 because it is coming out of the plane. So there will be no velocity in z direction. You only have velocity in x and y direction, right? So 1/2 m1 L1 squared theta dot 1 square plus, now we are going to involve the angular velocity because you have the inertia of this link there. So right now this is just one link. So for this first link, I'm just gonna write z1 theta dot 1 square, which is omega. So this, if I factor out theta dot 1 is 1/2 m1 L1 squared plus izz1 squared theta dot 1. Why is only izz? It's rotating in that direction, right? So it is basically, if you write in a matrix form, that's what's gonna come out. I just wrote it, right? If you go look back, it's a 3x3 matrix, but because you only have rotation one, the z direction, that's the only inertia that matters. All right, so how about K2? Yes, I'm gonna, let's keep it in, yeah, outside, that's easier, thank you. This the lazier way, yeah. Don't have to move everything. All right, so that was link 1. How about link 2? What are the velocities involved in the second link? So now you're moving your frame, you're looking at frame 2, right? So we want to know what kind of velocities you have at frame 2. The previous frame is a loop joint. Joint in frame 2 is a prismatic joint. What kind of velocities do we have? Yes.
We have both the velocity due to the prismatic joint and the velocity due to
Yes. Because when this is being rotated, the second joint is also rotating with it, right? What is the angular velocity? Theta dot 1, right? Just think that the length of the link got larger. It's rotating with the same. So we have one kinetic energy because of this rotation. Then it's a prismatic joint, so your center of mass is also moving longitudinally, right? In the direction of the prismatic, direction of 2. And so that's for the velocities. Now, how about the inertial tensor there? Do we have anything angular velocity applied on that link? It has inertia, right? So it would be I omega, which is omega theta 1, IC2 omega this time. But if this was a heavier object or a bigger object, the size and the former would impact the kinetic energy. So what does it mean is, so let's write it. 1 is 1/2 m2 d2 theta dot 1, right? Just gonna write a square like that, it's easier. d2 square theta dot 1 square. One is because this second link is rotating the theta dot 1. Then we have 1/2 m2 d2 dot 2 because of the velocity of the prismatic joint, right? So one is the rotation. Then we are gonna also include 1/2 izz2 theta dot 1 square. So there are 3 terms there. If I reorganize, maybe it helps better. This probably shows better. These 2 terms are because of the rotation of the first joint, right? So you have more links, more objects. Then this one is because of the prismatic, that has a linear velocity also. So this is our K1 and K2. So K becomes K1 plus K2, 1/2 ml1 square plus izz1 plus izz2 plus m2 d2 square theta dot 1 square plus 1/2 m2 d2 dot 2. How about U1? So U is the potential energy, right? So for that is going to be theta 1, this is L1, and if you want to find H, so M1GH, let's call it H1, which is M1G L1 sine of theta 1. That's the height. As your object is rotating, your center of mass is going higher, right? How to find that edge is L sine of theta 1. U2 is going to be M2G H2, which is M1G. This time, since we are measuring our D2 from the base frame, this is just going to be D2 sine of theta 1. So here, this is your H2. This is still moving with this is the same theta 1, because there's no other revolute joint between them. So U becomes M1G L1 sine of theta 1 plus M2 G D2 sine of theta 2, theta 1, sorry, I can write that as M1 L1 plus M2 L2 D2 G sine theta 1. So that's U. Now we already have this. Now we have to go to the EoM, equation of motion. I would say the easiest way is to start calculating these and then get the partial derivative, get the time derivative after you've done the first one. So partial of K with respect to Q dot. So if Q is theta 1 and D2, Q dot is theta dot 1 and D2 dot. So partial of K respect to theta dot 1, partial of K with respect to D2 dot. All right. This will give you, I'm just putting it in the matrix form. So this would be M1 L1 square, because we have K here from up there, plus I Z Z1. So you'll see that in this, in here, in K, only this term is is multiplied by theta dot 1 square, theta 1, right? So we won't, this will be 0, so we won't worry about that term when we're calculating the partial derivative. Plus I, what happened to my pen? Color. I Z Z2 plus MD2 square, and you see that 1/2 and 2 cancel each other out. I'm gonna write the theta dot 1 here, theta dot 1, and then K with respect to D dot 2, only this term has D dot 2 in it. 2 and 2 cancel each other, so it's M2 D2. So this would be partial derivative with respect to our Q dot. Now calculating this with respect to Q, which is theta 1, and then D2. This is D dot 2. Now here is a lot easier because you'll see that your K, your kinetic expression is not a function of theta 1. Yes.
Why didn't we subtract the potential energy?
So look at the potential energy. First of all,
Well,
yeah. So first of all, what I'm doing is I am doing them separately, and then when you look at your U is not a function of theta dot 1, so I'm not even bothering myself. So this is how you save time, right? Because you've done it before. but you can write it and then get the derivative and it becomes 0, right?
Should we be writing DL
Where?
instead of DK? Because we're trying to find the partial derivative of Lagrangian.
So here, let's do this. I'm gonna create a page.
Like, I understand that it's only going to be.
Yeah, I'm just being lazy and just writing the kinetic energy, but I'm gonna show you. You add page. Where am I? Add page. So when I look at my U, this doesn't have anything, but I can do that. I can say this whole expression K minus M1 G L1 sine of theta 1 Q dot, right? I can write that. And since this is Q dot, this is not gonna have any effect. That's why I didn't write it.
The partial.
Yes. So here I just took an easy way. So instead of, because I looked at my function, I know your gravitational force is never a function of theta dot or Q dot. It's always a function of Q, right? If you think about it, it's always function of your Q or your theta, your H. So when you are doing this part, basically that will always become 0. So you can take this out and it will become this is always 0. It's never a function of Q dot, so it doesn't, so I didn't write it. Okay. All right, so now we are doing, so let me write this one so you can see. So right, partial L with respect to Q, I'm gonna write partial K minus U with respect to Q, then partial K with respect to Q, minus partial U with respect to Q. Just opening it. So instead of getting the partial of a very large expression, I'm just breaking the smaller parts. So I'm gonna calculate partial of K with respect to Q first, which is partial of K with respect to theta 1, partial of K with respect to D2. Then I'm gonna say partial of U with respect to Q, theta 1, partial of U with respect to D2. Okay. And then I can deduct them from each other. Just I think it's neater this way. So that becomes 0. The first one is not a function of theta at all. And then the second part, respect to D2, we have D2 here. So there will be a term here, M2 D2 theta dot square 1. And then for U is G M1 L1 M2 D2 cosine of theta 1, because it was a sine, right? Sine theta 1. And then G M2 sine of theta 1, because this was just here. So this term, if you separate them, G sine, well, we already have their separated ones. This is not a function of D, so this would be, D2 would be 0. So I'm just considering this guy down below. Now that is that term. Now, one thing that I haven't done is this term has to be, you have to find the time derivative of that, right? Because the equation says time derivative of partial of Q, partial of L with respect to Q dot. So partial time derivative of d dt of, okay, Q dot, right? I haven't done that part yet, but if you look at here, they will do the double dot one, and then for the first one, and then m double dot two for the second one, right? So let's grab that. So this is the double dot, and then m double dot. I'm just getting the time derivative of that. So I have all of my terms. All I have to do is put them together. So we know that our tau was d dt which, because of our functions, it end up being d dt k now if you put them together, you're gonna get your tau 1 and tau 2, because this is your tau I, right? qi. You get your tau 1 and tau 2. I'll just write we know that at the end we're gonna get mq double dot plus some v q dot plus gq, right? This is equal to tau. So we will expect to get a M matrix that is 2 by 2. And it has to be multiplied by Q double dot. You see that double dot appeared here. So basically we are just writing the mass matrix. So M1 L1 square plus IZZ1. Just lots of calculation. It has to be a square, right? So this is 0, this is M2. Remember that MQ will be multiplied by Q double dot. So theta double dot 1, D double dot 2. We only have them appear here, so to write in the matrix form, if you don't have the terms, it's just 0 when you're writing matrix form. Hence, you have this 0. You see that this is symmetric, right? Then you have your VQQ, QQ dot is 2m squared d2 theta dot 1 d dot 2 negative m2 d theta dot 1 2, and g would be ml1 plus m2 d2 g cosine of theta 1 m2 g sine of theta 1. Basically just grabbing the coefficient. So by the time that you're done with this, you have everything. You can just grab it from there and create. So you always, when we say what's the equation of motion, that's what we do. So you have to put it in this form at the end. So we expect to see M, V, and G. Do you have a question? Okay, so I'm gonna pause this.